Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. We will continue our discussion in this video for the Bloch equation solution. Now we would generalize it to a more generic case where you could have an inhomogeneous object. By that we mean the T2 and T1 constants could vary or spatially, and also we are going to consider non-uniform field. Let me move back into the notebook mode. One word of caution here. When I say the magnetic field varying spatially, it doesn't mean I have the B component of this magnetic field in X, Y directions as well. I still have the magnetic component, applied magnetic component in the Z direction only, but this Z direction component value varies spatially depending on at which X, Y and Z locations I am. Okay, this has to be very clear. On BZ component is dependent on XYZ values, but still your magnetic field is there in the Z direction only. This is something that has to be absolutely clear to you. So as I mentioned, inhomogeneous object, by that we mean the T2 value varies now, okay, or spatially, that's something. And then non-uniform field means your, let's say now what we would do is we are going to use XYZ. For that, for a compact notation, I'm going to use an R bar vector, that's in fact a vector with components X, Y and Z. Now with the modifications that are coming because of inhomogeneous object are very trivial. Just I need to have, in place of T2 I will be having T2 of R bar. Now that's going could vary with the spatial location which is indicated by R bar. Now pay more attention to how this magnetic field is there now. Now this magnetic field is dependent on X, Y, Z as well as time, space and time as well. So this R bar is accounting for space, T is accounting for time. And make a note here, you have a Z cap here. This is all the amplitude of this vector in the Z direction. Okay, so you still have at every point your B value is there in Z direction only, but the amplitude of that vector, if you look at it, earlier in the previous class we had a uniform magnetic field, so we simply had B naught there. What is now we are going to newly add here is, let's call it as delta B of R bar comma T. There is a new function that we are adding here, delta B of R bar comma T. As the parameters of the function indicate, it is now delta B is the function dependent on X, Y, Z as well as T. That's what we are now going to take a look here. Okay, now we already have done enough things to analyze. When you have simply this term is 0, delta B of R bar comma T equal to 0, that we had already done it, right? So that gave us, for example, dm by dt is equal to, in that case, minus of 1 by T2 of R plus j omega naught. Again recollect, the moment we are saying m, this is a complex value mxy, if you recollect, so that's having mx plus j times my in the xy plane. So what we are concerned here is the analysis of the transverse magnetic field, right? So if you recollect the equation that we have derived in the last couple of classes about the transverse magnetic field, that's equivalent to minus of 1 over T2 Now in place of t2, now I am writing it as t2 of r bar, because this could vary with spatial location, plus j omega naught times m. This is when this function of delta b of r bar comma t equal to 0. Now this multiplied with m is the linear equation that you had. Instead of now this, you have an additional term of delta b of r bar comma t. What do you think would happen now because of this? Earlier it is rotating at a frequency of omega naught, right? Now when this is just b naught into z cap, gamma times b naught is what you had the value there, right? That's what with which it is rotating when you're, and now it will be rotating with, in addition, this also has a component of delta times omega of r bar comma t also, which is now gamma times b naught is this omega naught that you have it earlier. Just if you have b naught, gamma times b naught is what it is rotating. Now in addition to that, now you have gamma times delta b of r bar comma t. Okay, this is what you are writing as delta omega. This is the new term that you are getting it. To say it in another words, now the frequency at which it is rotating is spatially varying now, and that now has got modified into omega naught plus delta omega times r bar comma t. This delta omega times r bar comma t is equal to gamma times delta p. This is a very straightforward extension. Now you need the solution for it. Well, this is again pretty simple. Just pay attention here. This term, initially you have m naught, right? So what would happen if you recollect from the equations that we derived in the last class? What would be that if you consider these three terms, that's what we derived. Okay, of course t2 of r bar, just we added that now. Other than that, if you have an initial vector of m naught, that would be rotating with a value of omega naught radians per second. So that's why you have e power minus j omega naught t, and its magnitude is slowly coming down. It is decaying by a factor of 1 by t2. So you have e power minus t by t2 of r bar now. In addition to that, in the dm by dt, you have this term now. So when you are computing m, obviously what you do here, you take an integration here. Okay, so that integration has given omega naught being constant. You got here omega naught times t, but this being dependent on time as well. Okay, this omega is spatially dependent as well as time dependent. So what you have here now is e power minus j times the derivation. To that you take integration, then you get m here. So then when you do that, 0 to t delta omega of r bar times, since to just not to mess up with the variable t here, so you are integrating term here, you are calling it as tau, because anyway the upper limit is t here, right? If you want to compute its value at t, so this variable is changed from t to tau here, this t within the integration. So that's equivalent to integral over 0 to t delta omega of r bar comma tau, this function into d tau. This is what we decide on how we would like to vary our b, delta b, and you multiply it with gamma, you are going to get this function. So you integrate it over from 0 to t. That's going to tell you at what frequency spatially the frequencies are varying. This is something which is helpful for us in spatial encoding of the magnetic fields, right? This is the very generic expression. Now what we would do now for the rest of this lecture is we would consider now some specific functions for this delta b of r bar comma t. In what way would we like to vary this delta b, and then what would be the transverse magnetization field as a result of that particular function. That's what we are going to see here. Particularly we are going to see three special cases. First case, static gradient field varying with x value. Okay, so static gradient field, by that what we mean, this is not dependent on time, and then varying with x value. So spatial variation is with respect to x only. That means for a given value of x, everything would be rotating at the same value. So that would essentially give you the yz planes, okay, for different values of x. So now that should vary now for each yz plane. Okay, then how would we like to write that? As you move on along the x-axis here, this magnitude, you want it varying with a gradient of gx, which means the dbz by dx. Okay, again remember, this bz component could dependent on x, y, z as well, although this is its amplitude we are talking about. Vector is directed, direction is towards the z direction only. So what we are saying here is dbz by dx equal to gx. In other words, your delta b of r bar comma t is equal to gx times x. Hope that is clear. And then when you write the frequency for it, all you need to do is multiply it with the gamma. So that would give you gamma times g subscript x times x. This is the rate at which you are varying. Suppose this is your x-axis, the rate at which you are varying your gradient is given by this gx. Now all the unknown quantity is this thing, so let's compute this integral so that we will know the resulting value. It's varying from 0 to t. This value is equal to gx times gamma into gx into x, and tau varying with time. The variable, the time is varying from 0 to t, but you could notice here this has nothing to do with the t. So when you are integrating it with respect to time, this is a constant, so all you have is multiplication with the t. So then that value you substitute here, then what you are getting, the magnetization vector, transverse magnetization vector that you are getting is m naught into e power, this is how it is exponentially decaying with respect to tau. This is e power j omega naught t. Okay, that's with which it is rotating earlier. But now you could see for a given x value, okay, for each varying x value, this you could combine these two terms if you want. Then you could write e power minus j of omega naught plus gamma times gx into x, g subscript x times x, okay, into t. So now for every given x value, it rotates at a different frequency, at a different speeds here. Okay, that is what it is going to have an impact. So what it is telling you is the planes at different x locations, you could call it as yz planes if you wanted, because x is constant there, produces signals at different frequencies. So that's how in fact you would be getting, further you make certain modifications to your whole process while you are giving the RF signal itself, so that this gets excited, will be exciting that particular field, and that's how you would get response from that particular slice. So this is equation implies that planes at different x locations produce signals at different frequencies. Okay, and the rate at which this frequency varies is it varies linearly with respect to x. As you could see here, at any given location its value is omega naught plus gamma times gx times x. Gamma and gx are constant, right? So this varies linearly with respect to x. Hope that is clear. Now the second special case that we are now going to consider is why vary only the gray have values varying spatially with respect to x only. Let's have something which is still static. Static means this field is not going to vary with respect to time, but let it vary for both x, y and z. In other words, now at any given point you have the additional field delta b of r bar comma t is equal to gx times x plus gy times y plus zz times z. Okay, now again for the notational convenience, we use here the dot product representation, where my delta b of r bar comma t, I could write it as the dot product of this z bar with r bar, is it not? So that's what is your delta b of r bar comma t, delta b of which is a function of r bar and t. Now once you know delta B, how do you get the delta omega? You simply multiply it with gamma. So delta omega of r bar comma t is gamma times g bar dot r bar. Now again, what all you need to do to compute the m bar value? So here you substitute this value here. So delta omega in this place, gamma times, right, g bar dot r bar integrated with respect to time, which is varying from 0 to t. As again you could see here, this has nothing, this function inside this integral is independent of time, so it will have then multiplied with time once you integrate that. So that's what you are getting here, gamma times g bar dot r bar into t. So that's what the equation now, m naught into e power minus t, the same thing, the rest this is same as the earlier one. Now instead of here, if you have 1 gx into x you have there, now here what do you have, g bar dot r bar is nothing but gx into x plus gy into y plus gz into z. Now every location is now going to resonate with different frequencies, right? That's what is going to happen when you are varying the m value spatially with all x, y and z values. Last case we are going to look at is, this is for example where you are varying the gradient fields with the time. Okay, then what you have to do is, of course, you keep the whole thing as it is here, the way here, delta omega of r bar comma t. In that place what you have now is b naught plus gradients are varying with respect to t. So this function is what you need to give there. So this is nothing but now g bar of t times r bar. So earlier this function being only varying spatially, you had treated it as a constant and that's why you just simply multiplied with the t. Now all you need to do is you put that function there and you integrate it with respect to time analytically. Perhaps if your g bar of t you could express it analytically, you will get an analytical expression there, and that's what you are going to get as your m. Okay, hope this is clear, where we have made a transition from the previous lecture where we considered Bloch equation for a homogeneous object and a uniform field. Now we moved on to a even more generic case where in your object the t2 is replaced by t2 of r bar and your uniform field is of b naught is replaced by b naught plus delta b of r bar comma t, and then we considered certain special cases of it. Okay, hope that is clear. That's all for this video lecture, and see you in the next class. Thanks for watching. Bye, take care.